So this is more of a tutorial covering an example of a root locus sketch. I want to use the fundamental principles we have studied. So we are just going to look at one example. Okay, and so this example, for example, given a system like this, k 2s plus 3 all over s into s plus 1, s plus 2, s plus 4. Okay, and then of course you have this here minus plus, this is our r of s, and this is our e of s, and that is our c of s. Okay, so if we have this system, of course, then we can easily find a t of s and use it. Okay, so again, this is a system, the root locus for this system, okay, is going to be equivalent to, if the system was drawn this way, okay, k, okay, and then this is s plus 3 over s into s plus 1, s plus 2, s plus 3. Okay, so if it's like this, then it's going to be basically the same. Okay, now even if the function, the system was drawn like this, okay, and we had k here, s plus 3, s plus s into s plus 1, s plus 2, s plus 4. Okay, so if we had this system, okay, let me change this. So let's say this is s into s plus 1, s plus 2. Okay, this is k, and this is the h, 1 over s plus 4. Okay, then what I want you to understand is, again, for each of this, for this one, k gh will be equal to k s plus 3 over s plus s into s plus 1, s plus 2, s plus 4. Okay, if you come to this system, again, you see that k gh will be equal to k into s plus 3 over s into s plus 1, s plus 2, s plus 3. And if you come to this third system, you see that k gh once again will be equal to k into s plus 3 all over s into s plus 1, s plus 2, s plus 4. Okay, so this is s plus 4. Okay, yes. So comparing, in terms of root locus, you will see that the root locus for system 1 is going to be the same as the root locus for system 2, the same as the root locus for system 3. Okay, so the shape here doesn't change anything. Okay, of course, when you do the response, because of the location of the zeros, which is going to be possibly 0, different for them. Okay, because you see that the zeros will be this and that for this system. Okay, but then the zeros will be only this for this system and this for this system. Then it's evident that the zeros of 1 and 2 will be the same, but the zeros of 3 will be different. So for the behavior, the transient behavior will be refined by using the zeros. So in this case, their actual transient characteristic or specification can be defined by the poles, and therefore the root locus will be the same. So the root locus of these three systems, when they are drawn, they will not look any different, okay? But then their overall transfer function will be different for the three, because you see that it has different numerator polynomial. So let's look at how to plot the root locus. So we have been given kgh equals k into s plus 3 over s into s plus 1, s plus 2, s plus 4. So first, we have to find our poles. So our poles will be 0, -1, -2, -4, implies our number of poles equals 4. Our zeros will be -3, so number of zeros equals 1. Okay, so first we can go to the axis and plot our poles and zeros. Okay, and make it a little nicer. So 1, 2, 3. 1, 2, 3. Okay, so for the meantime, we are not dealing with 2, 3. So for the meantime, we are not dealing with any imaginary roots. Okay, so from here we can plot our poles. So this is 1, 2, 3, 1, 2, 3. Of course, I have to extend this and put 4 minus. Okay, and then of course we'll have the imaginary axis, but I'm not dealing with them right now, so I'll forget about that. So where our poles will be, our poles will be at 0, -1, -4, and -2. Okay, so those are the 4 poles: 0, -1, -2, -4. And our zeros will be at -3. Okay, so now if I want to plot my root locus, so first the principle says it's going to lie to the left of an odd number. Okay, so this is 1, 2, 3, 4, 5. Okay, so let me take this off, okay, so that we can see it clearly. Okay, so first, this is 1 is the first odd number, so it's going to lie here. 3 is the next odd number, so it's going to lie here. 5 is the next odd number, so it's going to lie here. Okay, then the next thing is, where is it starting from? It starts from a pole, so this will show these angles, and then it will start from another pole. So if I start this, also show another, and then this will show another. They will end at zeros. Okay, so this is 1, 0, so this one is ending here, and then the remaining ones, then one is going to infinity from here, and these two will also then go to infinity. Now where will the centroid be? So now I can compute my centroid. Okay, and that is summation of poles minus summation of zeros all over number of poles minus number of zeros. Okay, so summation of poles is going to give me 0 plus -1 plus -2 plus -4. So this will be 0 plus, so 0 minus 2, or -1 -2 -4, minus summation of zeros, that is -3, all over number of poles, which is 4 minus number of zeros, which is 1. So this is going to give me minus 7 minus 3. Okay, that's going to give me minus 7 minus 3 plus 3 all over 3, and that is minus 4 over 3, okay, which is minus 1.33. Okay, so in this case, what will be our angle? Theta A will be equal to K, 2K plus 1 times 180 all over 4 minus 1. So that's going to be 2K plus 1 over 3 times 180. And so it's actually, the angle is going to be 2K plus 1 times 60. Okay, and so when K equals 0, our angle is 60 degrees. When K equals 1, our angle is going to be 60 times 3, 180 degrees. And when K is equal to 2, our angle will be 60 times 5, okay, which is 300 degrees. Okay, so when we come here, you see that our centroid is at minus 1.33. Okay, so that is somewhere here. Okay, so let me draw the centroid with a different line, a different color. So it's here, and the angle for the first centroid is 60 degrees. The angle for the second centroid is 180 degrees. Okay, so usually we don't draw this so that it doesn't interfere. So that is going to be 180 degrees, but actually it's extending from here, and so that is 180 degrees as the angle. And then the third one is 300 degrees. Okay, so of course that is the same as 60 degrees in the reverse direction. Okay, but it's 300 degrees if you draw it here. So if you draw from here, that is 300 degrees. Okay, so this will be the asymptotes, and therefore how will the system behave? Of course, we only see the two systems here. Okay, so this means that this will start from here. When they crash, they will move here. Let me use the normal. So when they crash here, they will move along this line to infinity, and then when they crash here, they will move along this line to infinity. Okay, so that then becomes the root locus. So of interest to us, if you look at this root locus critically, are some particular points. So that's how the sketch of the root locus will look like. But there are some unknowns, or there are some values we don't know here. First, you see this real axis. This real axis. They are coming, one is projecting from here, the other is projecting from there. They crash somewhere here and they depart. Okay? Now, where they are departing, the exact value there on the real axis where they depart, we don't know. Okay? The second thing is, you see that they are crossing the imaginary axis here and there. Okay? The exact value where they cross the imaginary axis, we don't know. Okay? So these are two key points that we don't know, and we will need to actually calculate them. Okay. The second thing is, we have not dealt with, but if there were some poles here, then your system there will be root locus maybe originating from this pole, another one originating from this pole. Okay. If there were zeros here in the complex plane, one will arriving at this 0, arriving at this 0. Okay, so what angle do they arrive or depart? We don't know. So the first point we are interested in is they break off point. Okay, so this point where it breaks off from the real axis, or we call it, actually the technical term is breakaway. So the point where it breaks away from the real axis and enter into the imaginary space, we don't know. So we need to compute that. And if there were two zeros side by side, then you will get it coming and then leaving to the zeros. Okay, so in that case, we also talk about break-in point. So that will be break-in point. Okay, those ones we don't know, so we need to find that. So we'll find break away and break-in point. Second, where it crosses the imaginary. Okay, so J omega crossing points. Those ones too we don't know. And third, if there were imaginary poles, complex poles or complex zeros, then the angle of arrival or departure from them, the complex zeros and poles respectively, will also be not unknown. Therefore, the next lecture we are going to look at how to calculate the breakaway point, the break-in point, the J omega crossing point, and then the angle of departure and arrival. Okay, so that's what we'll do in the next video. Thank you very much.